And just like every other probability concept that we've talked about, it starts off pretty easy, and then all of a sudden it's like, oh, that's not easy anymore. So you just gotta kind of stay involved in the process. Right? So if you have 2 or more trials, we use what's called the multiplication rule. Okay. That's the key ingredient there. So multiple events means multiplication. It's as simple as that. All right. I think of the addition rule as the rule of OR, because it's most typically going to involve the word or in the framing of the question. But really more so, it's for single probability events. So one event with multiple possible outcomes. Right. So you flip one coin, you roll one die, right? You draw one card from a deck. Here we're taking 2 cards from a deck, or rolling a die twice, or flipping a coin twice. Right. So there's a little bit more going on, but not in a in too of an abstract sort of way. There are ways that you should be able to conceptualize still. All right. So we talk about tree diagrams when it comes to this, because in terms of coming up with a visualization of what's going on probability wise, tree diagrams are a useful tool. It's an organizational strategy more than anything else. And so with probability, you're going to find, and you'll tell me if I'm wrong about this, but I find it to be typically the case that the people who struggle with probability are the people who kind of struggle keeping their work organized. Right. And I'm not talking about like penmanship and highlighters and stuff like that. I'm talking about like just the flow of a solution to a problem. Like if you're the kind of person that has like part of your answer over here and another part over there and another part over here, and flip to page 32 on the back, you'll find the other part of that answer over there. And then look on the ceiling, you'll find another part of that answer over there. Like that's not a good organizational strategy. Right. And probability requires organization probably more than any other area of mathematics. Right. So tree diagrams and sample spaces go a long way towards making that happen. Right. So a coin is tossed and then a die is rolled. So we want to construct a tree diagram for a flip of a coin and then a roll of a die. All right. And then find the probability of tossing heads and rolling a die. Now I'll preface all of this by saying there's an easier way, and it's kind of written right below. So you have the easier way. It's just a matter of actually understanding why that easier way works. All right. So we'll start off with the flip of a coin. So when you flip a coin, there's 2 possible outcomes. You can get heads or tails. All right. So what we tend to do is just list the outcomes themselves rather than the probabilities that go along with them, at least in the early goings. There are other forms of tree diagrams where the probabilities get listed as well, but it doesn't really add too much to the conversation for us, because the way we handle probability, we don't really need to worry about that. All right. So we have 2 possible outcomes, heads or tails. So once I have the heads, then I roll a die. Once I roll a die, I can have upwards of 6 possible outcomes. And just as an FYI, it's more like a treat. Treat's not the right word. It's a good thing when I say that I always put, there's always a tree diagram question on the test. All right. So it's always there. So you can expect that there will be a tree diagram question. And the good thing about tree diagrams is that they can't be that complicated. Otherwise, it would just take you too long to construct them. So it's got to be fairly simple. Otherwise, it would take you the whole time allotted for the test in order for you to actually create the tree diagram. So it would have to be kind of simple along these lines. All right. So all you're doing is you're going through each outcome for each event and then following that up with whatever the next event is. All right. So my first event was that I'm flipping a coin, possible outcomes, heads or tails. Once I got the heads, then I'd say, okay, now I got a heads. All right. So what do I do now? Now I'm going to roll the die. All right. What are my outcomes when I roll a die? Numbers 1, 2, 3, 4, 5, or 6. All right. So then I go back to the beginning. I hit the reset button, start it all over again, and I say, all right, I'm flipping a coin. I got a tails. All right, I got a tails. Great. Now I roll the die. What do I get when I roll a die? Well, anything from 1, 2, 3, 4, 5, or 6. And that's my tree diagram. All right. We could put probabilities on here and it would make it look a little mathier, but this gets the job done because if all I'm looking for is a set of possible outcomes, then we got what we need. All right. So we're looking for the probability of tossing a heads and rolling a 5 specifically. Well, here's where I toss a heads and roll a 5. So it's assuming that we're following the branch where you rolled or flipped a heads in order to get to the pathway that leads you to a 5. So we have one pathway that satisfies heads and 5. We have 12 pathways overall. All right. So that would give us 1 over 12. All right. Now, you could also look at it and say probability. I mean, there's a reason why it's called the multiplication rule. Probability of heads and roll a 5 would be the probability of getting heads times the probability of rolling a 5. All right, so that's what I state down here, which in turn would be 1/2 multiplied by 1/6. Which would give you a result of 1/12. Right? Now, I don't want to say that, well, you would only use this approach for cases where like you don't know what the probability is, for example. Like, I don't know the probability of flipping a heads or rolling a 5. Well, if you didn't know those probabilities, then you probably weren't making the tree diagram anyway. What we use the tree diagram for is an organizational strategy for more complicated cases where instead of saying probability of flipping a coin and rolling a die and getting heads and a 5, it's, it could still be flip a coin or roll a die, but it's saying find the probability of getting a heads and either rolling a 5 or a number less than or equal to 2, and it's like, oh, this just got really complicated, but it's really not that complicated if you have a nice tree diagram. So actually, let me throw that example in there, and you know what? I'll make that a typo for somebody. I'll write the example, and then somebody can claim it for a typo bonus. All right, I'm just going to shrink this up a little bit so it's a little easier. All right, so example. probability of getting a heads and a roll of 5 or number, I'll say less than 3. That still gets across the idea of less than or equal to 2, but then I don't have to write the words less than or equal. All right, so we have 2 components here, the heads part of it, and then roll a 5 or a number less than 3. All right, so looking at my tree diagram, and you know what I'll do is I will copy paste. That first pathway, the same pathways are still fine, but then I would also have to include numbers that are less than 3. All right, so that would be this guy and this guy. All right, so I would have 2 additional pathways along my tree diagram. And honestly, if I were coming up with this solution using a formulaic approach, it would be a combination. I'd have to give it a little thought because it's a combination of addition rule and multiplication rule, right? So as opposed to counting pathways, I would have 3 possible pathways. So we look at the pathways as, and let me just show you real quick. Let me just do a little bit better job there. So here's one pathway would be following this line, going to the 1. That's one pathway. Then following this line and going to the 2, second pathway. And then following this line and going to the 5, that would be my third pathway. All right. So in the end, either way, you're going to get it. It's just a question of how much effort are you going to put in before you get it. The tree diagram's pretty easy to just kind of scratch out, but maybe that's not something you want to do. It takes time, build time, but you get 3 out of 12 in that for that particular question. Right. So a little bit more time to come up with a tree diagram, but the payoff is that the probabilities are really easy to come up with, as opposed to going the other way where maybe you don't create a tree diagram at all, but then your head's spinning while you're trying to come up with formulas and rules and stuff like that you could use to find the probabilities. All right, so just food for thought and bonus. When it comes to finding probabilities with the multiplication rule, we have 2 types of situations. We have the independent events and we have the dependent events. So independent events are cases where the second event occurring was not impacted by the fact that the first event occurred already, right? So, like for example, if I roll or I'll just keep it simple. If I flip a coin once, I can get heads or tails. If I flip a coin a second time, I can still get heads or tails. It doesn't matter what I got the first time I flipped a coin. It's still the set of heads or tails, right? So that would be an independent situation. But then there's other cases where, for example, if I'm trying to select people at random to be part of a group, like we're doing group work in a class, and I'm selecting individuals to be part of different groups. Once I select a person, that person is no longer available to be selected for another group. It's like the old, choosing teams at recess for kickball or whatever. Like, what are my chances of being selected first? 1 out of however many people there are. All right, now we're down to me and the other kid. The last 2 people to be picked for kickball. So now I have a 1 in 2 chance of being selected. Better probability, but the only reason there's a better probability of being selected is because everybody else has already been selected. All right, so the probability changed from, let's say, 1 out of 12 to, it's the same concept. It's still me being selected to be part of a team for kickball, but it went from 1 out of 12 to 1 out of 2 based on the fact that other people were selected to be part of the teams. All right, so that's a case of dependent events. Cards are really good resources when it comes to kind of evaluating, the probabilities behind dependent and independent events, because there's a lot we could do with them. And so that's where we're going to kind of focus. All right, let's see the chat. Right, exactly. Very good. All right, so 2 cards are drawn from a standard 52 card deck. The first card is not replaced before the second is drawn. Right, so that part of the phrasing of the question, that makes it dependent events. All right, so that one little statement there makes it dependent events, because I will know after one card is selected from the deck, I will no longer have 52 cards in the deck. So my probability of, let's say, getting a king is not going to be the same as it was before, because there's one less card overall to work with, right? It's the same idea as like selecting somebody to be part of the, recess, kickball, that kind of thing. All right. There were 12 people. One of them got selected. Now there's only 11. So I have a 1 in 11 chance, a 1 in 10 chance, a 1 in 9 chance, 1 in 8 chance. The probability changes every time a selection is made. All right. That makes it dependent events. So the first question, find the probability of getting a king and an ace in that order, that specific order. All right. So we'll focus on that. Probability of getting a king is going to be multiplied by the probability of getting an ace. Now, this notation is not something that everybody is going to love, but it's necessary. So we just kind of learn to appreciate it. Vertical line, king. And I'll write what it means right now. What this notation means is the probability, I'll actually write it in words, probability that the card selected is an ace, given that, all right, so that given that part, that corresponds with that vertical line. The previous card selected was a king. Ooh, that G took off on me. That was a sassy looking G. All right. So I'm going to shrink this down a smidge. Oh, I missed the D. There we are. I'll just shrink it all down. And then zoom in. All right. So that's what that notation means. Probability. Oh no, I was worried that I wrote it backwards. Yeah, probability that the card selected is an ace, given that the previous card selected was a king. All right. So what's happening here is we're tying this outcome to this outcome. Right. So we're assuming success. We're assuming that the card that we intended to get on our first trial, we actually got. Right. So if I said find the probability of getting a 2 and then a 3, I would always assume that the first card I selected was a 2, like I actually got the 2. And then now I'd be asking, all right, now what is the probability of getting a 3, knowing that piece of information? All right. So the diagram, which I don't have. Let me just copy it again. Oh, it's right there. You know what I'm going to do? I'm going to do a screenshot of it so I have it from now on. I mean, I definitely have it as a screenshot. It's just I want to have it available as a screenshot. Copy that, save to photos, and then bring it in. No good place to put it. I'll just make it super tiny and then just zoom in. All right, so kings. Got 4 of them. All right, yeah. Those are my kings. So that's 4 out of 52. So then what I want to do is I want to assume that I got one of those kings. All right, so it could be anything. It could be the king of hearts, king of diamonds, king of spades, king of clubs, any one of those 4. So we assume that we got one of those kings, right? So assume we got one of the kings on the first trial. All right. What that means is that there is only 51 cards left in the deck. All right. There were 52, but I got one of the kings. So what I can do, like just arbitrarily decide which one you want it to be. Let's say I got the king of spades. So that card is gone. It's without replacement. So once I make note of what the card was, I don't then put it back in the deck, shuffle it up, and select again. I toss that card and then select from the deck, right? So there's only 51 cards available now, right? But I am still looking for the probability of getting an ace, right? So probability of getting an ace is going to correspond to these cards, right? Which in turn is going to give us this numerator, right? So there are 4 cards. The fact that a king was removed from the deck did not impact the number of aces that were in the deck. It only impacted the number of cards overall. But the probability of getting an ace has changed. Normally it would be 4 out of 52. Now it's 4 out of 51, right? So then I multiply and I have my probability of 16 over 2652. So you multiply top, top, bottom, bottom, and you get it. So it's really just the bottom values that you need to multiply. I've done card related probabilities so frequently that the number 2652 and the number 2704, they stick out in my mind as 52 times 51 and 52 times 52 respectively. So yeah, but you could just pop it into your calculator. 4 over 52 times 4 over 51. You get that hideous looking decimal there. But again, just tap on the fraction icon there and it'll simplify it for you. You don't need the simplified values. You could just multiply top, top, bottom, bottom. But if you want to put the simplified form because the calculator is giving it to you, that's fine too. All right. There's no requirement that you simplify your fractions. That's something to keep in mind. All right. So then the last one that we're going to do tonight, the king and ace in either order. Little formatting issue here. You can see how the font got a little wonky with numbers 1. Actually, all the problems on this page. I'll take those as typos if somebody wants to submit. Right. So king and an ace in either order. All right. So what that means is that we're looking at the probability of getting a king, then an ace, or probability of an ace than a king. All right. So we already figured out the first one, king and then an ace. We already know that, but just for giggles, I'll do it again. All right. So we have probability getting a king multiplied by the probability of getting an ace given that we had a king. All right. So same expression, just more shorthand notation. All right. Now the or. Well, or is consistent with the addition rule. It's the rule of or. So that means I'm going to add probabilities. Or also serves as kind of a reset button where it's saying, well, it's not going to be both of these situations because I'm only selecting 2 cards from the deck. Contextually, I'm only selecting 2 cards from the deck. So it's either going to be, the king and then the ace, or it's going to be the ace and then the king. Right? So it's not going to be both happening simultaneously. It's going to be one or the other. So this is the classic definition of or as a choice rather than or as a set of all possible outcomes in a set. Right? Set of outcomes in a set. Yeah. It's late. So probability of ace multiplied by the probability of getting a king given that the first card selected was an ace. Now, the tree diagram that you would draw for this would be monstrous, so we don't want to get into that. What you could do instead is just go back to the diagram, not the tree diagram, but the diagram of the deck of cards and just evaluate it that way, and just kind of take a look and see what's going on. Like, for example, we know that there are 4 out of 52 cards in the deck, so that are related to kings. So you would get that not by memorizing that fact, but by looking at the breakdown of the deck of cards. How many of them have the letter K on them? 4 of them. How many are there in total? 52. Right. The second part is the part if you're going to get jammed up. This is where it's going to happen. And it really doesn't have anything to do with the concept of it. It has to do with the notation. Right. Because if you're anything like me, not to say that that's a good thing or a bad thing, but when I was a student, every now and then I'd zone out a little bit and be like, all right, what just happened? Where did this A vertical line K come from? All right, I guess I'm failing this class. It's just how it goes, So the notation is the moral of the story there. The notation, if you're going to get jammed up, that's what's going to happen because the underlying meaning is not an issue. This is saying the probability of getting an ace as a card, knowing that the first card that you selected was a king. All right. So one of those cards, one of those kings was the card that you selected. All right. And I assumed it was the king of spades, but it could have been the king of hearts, king of diamonds, or the king of clubs. All right. Now, with that card removed from the set, there's only 51 cards left, but my full complement of aces are all available, right? I have all 4 of my aces. So I pop that 4 in there and we're good to go. And that's the same computation from before, 16 out of 26, 52. But then we have that added component there where we look at it from a different perspective. We say, what's the probability of getting an ace? 4 out of 52. We're starting fresh. In general, 4 out of 52. There are 4 cards that are aces. There are 52 cards overall in the deck. Right? So I can get rid of this now and say, all right, now let's assume that we got the ace. That card that we selected was an ace. And let's say that was the ace of diamonds. All right. That's not going to impact how many kings there are in the deck. Right. As far as kings are concerned, let's go purple for those keeping score at home. I still have my 4 kings available, but we did reduce the overall quantity of the entire set from 52 to 51. All right. So in doing so, we improved the chances of getting a king. You know, it's kind of like, I mean, I don't know how many of you have experience with poker or other games of chance, but, you know, like if you're hoping for a card to come up, it doesn't even have to be like a gambling game. It could be something like Monopoly with the community chest and the chance cards and stuff like that. You know, like you're hoping for a card to come up. So every time one of your opponents gets a card that you don't want, you're like, all right, good. I didn't want that card anyway. So that increases your chances of getting the one card that you do want, right? So there are 51 cards overall, and you can see the 2 probabilities are the same, both at 16 over 2652, which means that the ordering, because there were 2 possible ways in which you can order these outcomes, king then ace or ace then king, all it did was it served to double the possible outcomes that, you know, I'm sorry, double the probability, double the outcomes, but double the probability, in which case you get 32 out of 2652. Right. And then it begs the question of like, okay, under what circumstances will we want to do one as opposed to the other? The short answer is in cases where you don't care about the order of the cards, you just care about getting the cards themselves. You know, if you're going to draw 2 cards from a deck, I need a king and I need an ace. I don't care if the king comes first or the ace comes first. I just need those 2 cards. But if I have to bet on each card as they come out, you know, like hold them, you know, so the next card comes out, and I gotta put more money in the pot. If I get the ace as opposed to the king, that might influence how I make my wager. All right. Let me take a look at the chat here. I saw some things come in. Yeah, exactly. All right. So I'll pop a couple of stars on these remaining questions, because it's just like those other probability questions for the rule of or, where it's like I can keep talking, but it's not going to help if you don't get some practice with this on your own. You don't try it on your own first. Right?
Can you use that notation with more than 2 options? Can I do?
Say it one more time.
Sorry.
Say it one more time. Sorry, I didn't
use that notation with more than 2 selections. Can I do like ace, line, king, line, jack to do jack, then king, then ace? Or is it only for 2 things?
It's only for 2 things, but if you have a third one, then what you would do is you would, in your third trial, you would reference the previous trial.
Okay.
So you would say, let's say the next one you wanted was a queen. You would say a queen given an ace. And that would tie right back to the fact that the previous one was an ace, which was tying back to the previous one being a king. You know, so it's kind of like a sequence in that regard.
Cool, thank you.
Yeah, no problem. All right, so next class we'll pick up. We'll go over those problems because we'll have to hit those again, and then we'll extend from there. But like I said, practicing with these concepts is critically important as we go forward. Question?
Number 3, the probability of 2 cards of the same suit. Would it be the ace and the king? Or it would be 2 aces?
The suits would be like clubs, diamonds, spades, and hearts. Oh, so like 2 hearts or 2 diamonds and so on.
Okay, thanks.
No problem.